Welcome to calculus. Fractions will pop up when you least expect it. On this episode, Stevenson will demonstrate
I want to demonstrate to you a problem on how our fundamental theorem of calculus can be questioned. And it really gets you to think about different concepts that we've been studying majority of this year. So let's look at the following problem. It says the graph of a continuous function f with the domain of 0 to 8, so its closed interval, is shown below. So this is the graph of f. Let h be the function defined by h of x equals the integral from 1 to x of f of t dt. And then what I have for you is a series of 5 questions. Before we can begin answering questions, we first need to know how to interpret this graph. Well, this is where the fundamental theorem comes in. If h of x is the integral of f, then what is h prime? H prime is f of x. And what would h double prime be? That would be f prime. Now, how do I know this? If I apply the fundamental theorem here, h prime would be the derivative of the integral, right? Which we know the derivative of the integral are inverses, so we're left with this relationship. So what we want to do on our graph here is say that f is h prime. So this is really a graph of h prime. How do I know that? Because of the fundamental theorem of calculus. That is key and so critical in this analysis here. Let's look at our first problem here. Find h of 1. Okay, well, h of 1. H of x is defined as an accumulator function of f. So really, if I do h of 1, I'm just putting 1 into x here. So this says the integral from 1 to 1 of f of t dt. Well, that's just 0, right? That's one of our properties, right? If the bounds are the same, then there's no area. All right, let's move on to the next one. That seemed pretty simple. Is h of x positive or negative? Justify. Is h of 0 positive or negative? Let's set up the problem similarly to A. H of 0 would be the integral from 1 to 0 of f of t dt. Well, we'd have to switch the bounds of integrations to calculate this, wouldn't we? So that's really negative 0, 1 of f of t dt. And since we know this is the graph of f, if we're actually looking at this area from 0 to 1, we can see it's above the x-axis, right? But because we had to switch the bounds to get it, we actually know our area would be negative. So really, we would say h of 0 is negative because we had to integrate from left to right, from right to left. That's what the negative comes from. Let's move on to C. Find the x values for which h has a maximum. In order to determine extrema, we need to know what h prime is, correct? Well, good news, we have h prime. So let's actually chart this graph. So this is the the graph of the derivative of h prime. So if we do a chart from 0 to 8, now this is a closed interval of a continuous function. And if I have a closed interval on a continuous function, then I'm guaranteed my extrema, right? A max and a min. That's the extreme value theorem. So if this is my derivative graph, I'm going to just chart the behavior here. I can see it touches the x-axis at 1, 4, and nowhere else. So on the interval from 0 to 1, it's above. So I'm looking at the location of the points because this is the graph of the derivative. So it's above. From 1 to 4, it's still above, and from 4 to 8, it's below. So find the values at which h has a maximum. Well, I can see it's going to happen at 4 because this changes from positive to negative. Now look at the next part here. This says find the x values for which h has a minimum. Well, again, I'm going to look at my first derivative. Okay, so I just look at the location. I don't really see a change in behavior here from negative to positive, so I gotta look at my ends. At this endpoint, if the function has a positive slope, then that means from this point the graph is increasing. If I look at this end here, the slope is negative. That means the function is decreasing towards that point. So if you look at your derivative test, your first derivative test, we would know that these are possible candidates. So what we have to figure out is what is h evaluated there. So if I evaluate h at 0, I get the integral from 1 to 0 of f of t dt. Now, we already know that's a negative number, right? Because of what we figured out here. Well, what's h of 8? So that's the integral from 1 to 8 of f of t dt. Well, if I just look at my picture here, I can see that I have a little bit of positive, but then I have a lot of negative here, right? So the question becomes, which one is more negative? Is h of 0 going to be more negative, or is h of 1 to 8 going to be more negative? So from 1 to 0, I know I have just a tiny bit of negative because of what we learned over here. But if I do from 1 to 8, I'm going to have a lot of negative because this area will affect a piece of this, but I'm going to have a lot left over. So this tells me, purely by basing on the size of what I see in my graph here, that x equals 8 is going to give me my minimum for my graph. Now let's look at the last one. Find the x values for which h has points of inflection. So points of inflection require the second derivative. Okay, let's go back up to here. We know h is the integral of f. That means h prime is f. But that means h double prime is f prime. So if this is the graph of f, which really represents h prime, then I need to do the derivative of f to get h double prime. That's what this says. So I need to now look at the slopes or behaviors of this. So let's do a sign chart. When will the slopes be 0 here? It'll happen at 1, it'll happen at 3, and it'll happen at 6. Okay, now let's chart the slopes. So from 0 to 1, it's decreasing. From 1 to 3, it's increasing. From 3 to 6, it's decreasing. And from 6 to 8, it's increasing. So I can see that 1, 3, and 6 are candidates for points of inflection. But remember, the sign of the second derivative at those points must change to actually consider them points of inflection. Well, I can see the sign changes at 1, at 3, and at 6. So all three of those are candidates or are actual points of inflection.